Gravitational field. Gravitational field is produced by all objects with mass. So if an object has mass, then it can produce gravitational field. The gravitational field strength of the Earth is 9.8 Newton per kilogram. So gravitational field is measured in Newton per kilogram. Electric field. When we talk about electric field, we are referring to a region where charged objects experience a force. Charged objects experience a force. That gives us an electric field. So an electric field strength can be calculated by dividing the force by the charge. Magnetic field. Magnetic field is the space around a magnet where the magnetic forces work. And magnets can attract or repel magnetic substances within a magnetic field. So the space around a magnet where the magnetic forces work, where the object experiences the magnetic force, then we refer to that space as magnetic field. A magnetic force is the attraction or repulsion that occurs between electrically charged particles due to their movement. Magnetic force is the attraction or repulsion that occurs between electrically charged particles due to their movement. We can use this equation to calculate the force on a wire. F equal I BL sin theta. So I is the current, B is the magnetic flux density, which is measured in Tesla. Then L is the length and the angle theta. Now we can have a special case, that is for the force to be maximum, then we must have theta to be equal to 90 degrees. So in that case, we will have the force to be equal to magnetic flux times the current times the length, because we plug in sin 90, we plug in 90 for theta, and sin 90 will give us 1. So we are left with this relation when the force is maximum. Then when the force is 0, it occurs when the wire is in the direction of the magnetic field or is parallel to it. We have this question here from Wasi, May, June 2012. Define magnetic line of force. A magnetic line of force is defined as an imaginary line in a magnetic field along which a free or isolated north pole would move. The line of force magnetic line of force is defined as an imaginary line in a magnetic field along which a free or isolated north pole would move. Then we have this one too, also from WASI May June 2012. A wire of length 10 centimeters carrying a current of 4.0 amps is placed between the poles of a powerful electromagnet of magnetic flux density of 2.0 Tesla. Calculate I, the force on the wire when it is powered to the field. II, the maximum force on the wire. III, force on the wire when it makes an angle of 60 degrees with the field. So let's see how we can quickly calculate that. So we saw that the force is calculated using the relation force, which is measured in Newton, equal the current in amperes times the magnetic flux density times the length, then times sine theta, where theta is the angle the wire makes with the field. So now let's see. The first part says that the force on the wire when it is parallel to the field. So in that case, we know that the angle there will be 0. So theta will be 0 because when it is parallel, then there's no angle between the wire and the field. Then the wire will make an angle of 0 degrees with the field. So we substitute 0 here to obtain, so the I part, for the I part, theta must be equal to 0. And this implies that the force will be equal to the current is 4.0 amps, so 4.0 times the magnetic density flux, which is 2.0, times the length, which is given as 10 centimeters. But we need to convert this to meters, and that will give us 0.1 meters times sine 0. Now we know sine 0 is 0, and when we multiply everything by 0 here, we get, or we can simplify further to obtain, 4 times 2 times 0.1 times 0 will give us 0 newtons. 0 newtons. Now let's look at the II part. The II part. For the II part, the force is maximum when the wire makes an angle of 90 degrees. That is, it is perpendicular with the field. So 90 degrees with the field. So let's substitute theta equal 90 over here to get our force to be equal to, so this is the II part, this is the II part. Our force will now be equal to the current, which is 4 times the magnetic flux density, which is 2.0, or simply 2 times the length, which is 10 centimeters. In meters we have 0.1, then times sine 90. And we know sine 90 is equal to 1. So the whole thing here will give us 4 times 2, which is 8, times 0.1. That will give you 0.8, 0.8 times 1 Newton. 0.8 times 1, and which will finally give us 0.8 newtons. Now we move on to the third part, I. Force, we are supposed to calculate the force on the wire when it makes an angle of 60 degrees with the field. So we have the I part. In this case, we put theta to be equal to 60 degrees. So that will give us the force to be equal to the current, which is 4. The current is 4 amps times the magnetic flux density, which is 2.0 Tesla. So times 2, then times 10 centimeters, convert to meters, which is 0.1, then times sine 60, times sine 60. Now let's simplify this. This will be equal to, this will give us 4 times 2, 8 times 0.1, which is 0.8, times sine 60. So 0.866, 0.866, and that will be equal to 0.69 newtons. 0.69 newtons. An oil drop carrying a charge of 1.0 times 10 exponent negative 19 coulomb is found to remain at rest in a uniform electric field of intensity 1200 newtons per coulomb. Calculate the weight of the oil drop. So this is from Wasi May June 2016. we saw that the electric field strength is equal to the force over the charge. So E is equal to the force F over the charge Q. So we know that the force in this case is the weight. The force in this case is the weight. The Q is the charge and the E is the electric field strength. So we can solve for the force to get F, or the weight, which is equal to the force, and that force is equal to the electric charge, the electric field strength E, times the charge, which is Q. So let's do the substitution to obtain the weight to be equal to, we're given that the electric field charge, which is measured in newtons per coulomb, is 1200 newtons per coulomb. So we have 1200 over here. Then times the charge, which is 1.0, times 10 exponent negative 19. So this is the same as 1.2 times 10 exponent 3. So this will be equal to 1.2 times 10 exponent 4, rather, not 2, 10 exponent 4. First we move this 1, 2, 3, 4. Then times 1, which is the same as 10 exponent negative 19. So we multiply these, and since the bases are the same, we subtract the exponent, and that will give us 1.2 times 10 exponent negative 15 newtons. 10 exponent negative 15 newtons. So that is the weight of the oil drop.